But we're talking about hundreds of millions of times the mass of the sun. But it's a black hole, so it's small for that much mass.
Wow.
The sun goes around a black hole in the constellation Sagittarius at the center of the Milky Way galaxy.
Scientists have made a jaw-dropping discovery right at the heart of these enigmatic cosmic beasts. They've unearthed something mind-blowing and terrifying inside a black hole, challenging everything we thought we knew about these cosmic wonders. Buckle up, because we're about to unveil the astonishing secrets lurking within a black hole's mysterious core. Are you curious to know more? Let's dive in. Black holes are a fascinating phenomenon. You see, according to a brilliant scientist named Albert Einstein and his theory of general relativity,
the surface gravity is so high that you cannot escape it, even at the speed of light. You are forever trapped.
Gravity is not a force like magnetism or pushing and pulling. Instead, it's a result of how space and time are curved or bent by objects with mass and energy. Imagine you have a massive object, like a star, in space. It has an enormous amount of mass and energy, and this causes a deep dent or curvature in the fabric of space and time around it. This curved space and time is what we call a gravitational field. The more massive and energetic the object is, the stronger its gravitational field and the deeper the dent it creates. Now, keeping that theory in mind, let's talk about black holes. They are some of the most extreme objects in the universe, with unimaginable amounts of mass and energy packed into a tiny space. They have so much mass that their gravitational field becomes incredibly intense. This intense gravity creates a super deep and very strong dent in the fabric of space and time. Here's where things get really crazy. The gravitational pull near a black hole is so incredibly strong that it forms what we call an event horizon.
That the event horizon is not some wall, it's just space moves smoothly through and across the event horizon.
This is like an invisible boundary or point of no return. Once something, like an unlucky spaceship or even light, crosses this boundary, it can never escape the black hole's grasp. It's as if the black hole has an invisible force field that holds everything inside, including light, which is usually the fastest thing in the universe. Just to emphasize how extraordinary this is, imagine you're shining a flashlight. The light beams travel really fast, about 300,000 kilometers per second. But if you were somehow inside a black hole, the speed you would need to escape its clutches would be even faster than the speed of light. That's impossible according to our current understanding of physics. So, any light that enters a black hole becomes trapped forever, unable to break free.
Light into the black hole. Light coming from farther away gets bent around it.
So, when we talk about a black hole, we can't forget about its mysterious boundary called the event horizon. It's like a point of no return for anything brave or unlucky enough to venture across it. Once something crosses that boundary and falls into a black hole, it's a one-way trip with no turning back. The event horizon isn't something you can physically touch or see. It's more of a mathematical concept that tells us where we can no longer observe what's happening. You might be wondering, how big is this event horizon? Well, it all depends on the mass of the black hole itself. The more mass a black hole has, the larger its event horizon will be. Scientists came up with a formula to calculate the radius of the event horizon, and they named it the Schwarzschild radius, after an astronomer named Carl Schwarzschild, who figured it out back in 1916. To find the Schwarzschild radius, you divide the mass of the black hole by a constant that involves the gravitational constant and the speed of light. For example, if we had a black hole with a mass 10 times greater than that of our sun, its event horizon would have a radius of about 30 kilometers. In the heart of a black hole is what is known as the singularity. All the mass and energy of the black hole, no matter how mind-bogglingly huge, is squished and compressed into an infinitely tiny and dense point at the center. We call this point the singularity. It's like a cosmic heavyweight, packing an incredible punch of gravity and curvature. In fact, the singularity has infinite curvature and infinite gravity, which is pretty fascinating. But here's the catch. Our understanding of physics starts to crumble when we try to make sense of what happens at the singularity. We simply don't know what goes on there. It's as if the laws that govern our universe take a break or go on vacation, leaving us scratching our heads in wonder. Scientists are still exploring this enigmatic territory, hoping to uncover the secrets hidden within the heart of black holes. And how do black holes come into existence? You know, it all starts with the life cycle of a massive star. These stars are like cosmic powerhouses, fueled by incredible nuclear fusion reactions happening deep within their cores. Imagine these reactions as a fantastic cooking show.
A specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
Where hydrogen atoms combine to form helium atoms, releasing an enormous amount of energy in the process. Now, as long as the star has enough hydrogen fuel to keep the fusion going, it remains stable. But stars are greedy, and they want to keep the fusion party going. When they run out of hydrogen in their core, they get a little creative. They start fusing heavier elements like helium, carbon, and oxygen. Each fusion reaction with heavier elements produces less energy than the previous one. To compensate for this, the star has to work harder and burn faster, turning up the heat to maintain its delicate balance. And sadly, every star's journey must come to an end. The star reaches a critical point where it can no longer fuse any more elements. At this moment, something extraordinary happens. The star's core collapses under its own tremendous weight, like a magnificent implosion. And there you have it, a black hole is born. When the core collapses, it forms the heart of the black hole called the singularity, which we talked about earlier. This singularity holds all the star's mass and energy in an incredibly tiny space, creating an intense gravitational pull that not even light can escape. It's like a cosmic vacuum cleaner, sucking everything into its gravitational embrace. And when a star is approaching the end of its life, what happens next depends on its size, or in other words, its mass. Let's break it down into 3 stellar weight categories. First up, we have stars that are smaller than about 3 times the mass of our Sun. These stars are in for a transformation. Instead of going out with a bang, they become something called a white dwarf. It's like the star decides to retire gracefully. Inside, it's a dense ball made up of carbon and oxygen atoms, which continue to emit light as residual heat. Now, if the star happens to weigh between about 3 and 20 times the mass of the Sun, get ready for an explosive spectacle. These stars go out with a massive supernova bang. The core of this star, amidst the chaos of the explosion, undergoes a dramatic collapse. It becomes a super dense ball known as a neutron star. Imagine squeezing up to 2 times the mass of our Sun into a tiny sphere with a radius of only about 10 kilometers. Now, if we're talking about a real heavyweight star, there are ones that weigh more than about 20 times the mass of the Sun. These stars also explode in a supernova, just like their slightly lighter counterparts. However, the core of these mammoth stars has a different destiny. It collapses under the weight of its own gravity, and it doesn't stop there. The gravity becomes so incredibly intense that the core shrinks down to 0 volume and infinite density, which again results in the birth of a black hole. Black holes have a couple of types. We have stellar mass black holes. These are the ones that form from massive stars nearing the end of their stellar journeys. They typically have masses ranging from a few times to several tens of times that of our dependable Sun. Stellar mass black holes are actually quite common in our galaxy and other galaxies out there in the vastness of space. Now, let's shift our gaze to the colossal supermassive black holes. These cosmic behemoths are the true giants of the black hole family. They boast masses that are millions or even billions of times greater than that of the Sun. Picture them as the masters reigning at the centers of most large galaxies, including our very own Milky Way. These mighty black holes are thought to have formed during the early stages of the universe, born from the collapse of massive clouds of gas and dust, or from the merger of smaller black holes. Their presence greatly influences the evolution of galaxies, shaping the formation of stars and planets that dance around them. Now we come across a rare breed known as intermediate mass black holes. These elusive creatures sit right between the stellar mass and supermassive varieties in terms of mass. They are like the middle children of the black hole family, somewhat mysterious and not commonly spotted. Their origin is still a bit of a puzzle, but scientists speculate that they may have formed from the collapse of incredibly massive stars during the early cosmic eras, or from the union of stellar mass black holes in dense and bustling star clusters. Lastly, we have the intriguing primordial black holes. These are the potential relics from the very beginnings of our universe, born shortly after the Big Bang itself. They emerged from fluctuations in the density of matter and energy during those cosmic early moments. Primordial black holes come in a wide range of sizes, from minuscule ones with masses just a fraction of a gram to massive ones thousands of times heavier than our Sun. It's important to note that while they are a captivating idea, primordial black holes remain hypothetical and have yet to be directly observed. Black holes have another interesting aspect: their rotation. For instance, there are the Schwarzschild black holes. These are the simple and straightforward ones. They don't spin. Think of them as the calm and steady black holes of the bunch. They are described by the Schwarzschild solution, a mathematical description in Einstein's theory of general relativity. These black holes have a nice spherical event horizon, which is like a boundary that marks the point of no return, and a singular point at the center called the singularity. It's like a singular dot with an immense gravitational pull.
In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future.
Next, we encounter the Kerr black holes. These ones are all about that spin. Kerr black holes are described by the Kerr solution in general relativity. They have an oblate or slightly flattened event horizon and a singularity that takes the shape of a ring. The rotation of a Kerr black hole creates something called the ergosphere. This region around the black hole is like a cosmic whirlpool, where space and time get dragged along by the spinning black hole. Now let's meet the Kerr-Newman black holes. These are the rock stars of rotation, with a little extra something. They not only spin but also carry an electric charge. Kerr-Newman black holes are described by the Kerr-Newman solution in general relativity. They share many similarities with Kerr black holes, like their oblate event horizon and ring-like singularity. However, the electric charge adds a twist to their story. The event horizon and singularity get a bit distorted by the electric field. And scientists have discovered ultramassive black holes. You see, an ultramassive black hole is a truly extraordinary cosmic heavyweight. It tips the scales at more than a whopping 10 billion times the mass of our trusty Sun. We're talking about a black hole that's so massive its gravitational pull is unimaginably strong. Anything that ventures too close to it would be in for a wild ride. Now, how did we even discover these cosmic monsters? Well, a group of sharp-eyed astronomers from Durham University in the UK took on the challenge. They utilized a cutting-edge technique called gravitational lensing. It sounds fancy, but it's actually quite fascinating. You see, according to Albert Einstein's brilliant theory of general relativity, massive objects like galaxies or clusters of galaxies can bend and distort the path of light. Using this gravitational lensing technique, the team of astronomers detected the telltale signs of an ultramassive black hole.
I personally think that we're actually looking at monster black holes where perhaps new laws of physics are emerging.
They observed the incredible bending and magnification of light caused by this cosmic heavyweight. This groundbreaking discovery not only revealed the existence of ultramassive black holes, but also provided further confirmation of Einstein's theory of general relativity. This discovery was made using the powerful Hubble Space Telescope. Our intrepid astronomers set their sights on a galaxy cluster called Abell 1201, which resides 2.7 billion light-years away from us. Now, here's where things get really fascinating. As they gazed into the depths of space, they noticed something peculiar, a giant arc of light encircling the cluster. But that arc wasn't just any ordinary light show. It was actually the distorted image of a faraway galaxy, all stretched and smudged due to the gravitational forces exerted by the cluster. So, how did they unravel this cosmic puzzle? Well, they called upon the computational power of supercomputers to simulate how light travels through the vast expanse of the universe. By carefully reconstructing the shape and brightness of the background galaxy, they were able to estimate the mass and location of the object responsible for the lensing effect. And guess what they discovered? They found an ultramassive black hole lurking in the heart of one of the galaxies within the cluster. This black hole weighed in at a staggering 30 billion times the mass of our trusty Sun. That's one of the largest black holes ever observed in the entire universe. And to top it off, this incredible discovery marked the first time a black hole was detected using the gravitational lensing technique. This finding highlights the incredible power of gravitational lensing. It's like having a cosmic magnifying glass that allows us to observe and study objects that would otherwise remain hidden or too faint to detect directly. This technique opens up a whole new world of possibilities for unraveling the mysteries of black holes and other exotic entities lurking in the depths of space.
For instance, if you see the example of gravitational lensing, you can use what you see to determine the mass of the lens. And this leads to an amazing use for the idea of gravitational lensing. We can use it to see the unseeable.
But this ultra-massive black hole throws a curveball at our current understanding of their formation and growth in the early universe. You see, its sheer size is so insanely massive that it challenges the conventional idea of how black holes evolve over time. To reach such a colossal mass of 30 billion times that of our Sun, within just 13 billion years since the Big Bang, it would have needed an extraordinary rate of accretion. Think of it as a supercharged feeding frenzy, attracting matter at an astonishing pace. Alternatively, it might have formed through dramatic mergers, joining forces with other black holes in cosmic collisions. This discovery opens up exciting avenues for studying the cosmic processes that shape these enigmatic cosmic giants. However, this exceptional ultra-massive black hole provides us with an incredible opportunity to put Einstein's theory of relativity to the test under extreme conditions. You see, these cosmic monsters push the limits of our understanding of gravity, and by studying them, we can examine whether Einstein's theory holds up in the most extreme cosmic environments. It's like conducting a cosmic experiment that probes the very fabric of space and time itself. Lastly, this discovery offers a tantalizing chance to explore the nature and properties of dark matter. Dark matter is a mysterious and invisible form of matter that makes up the majority of the mass in our universe. By studying the behavior and interactions of ultra-massive black holes like this one, we can gain insights into the distribution and influence of dark matter, shedding light on its elusive nature. And gravitational lensing is like a cosmic magic trick that happens when space and time team up with mass to create fascinating optical illusions. Here's how it works. According to Einstein's theory of relativity, mass has a profound effect on the fabric of space and time, causing it to curve or warp around itself. Think of it as mass creating a dent in a trampoline. Objects passing nearby will follow curved paths due to this warping. Now, light, which normally travels in straight lines, is no exception to this cosmic phenomenon. When light encounters a massive object, such as a galaxy or a cluster of galaxies, it gets caught up in the gravitational warp and follows curved paths as well. This is where the magic of gravitational lensing comes into play. Imagine you have a background source of light, like a distant galaxy or a star. As its light travels across the universe towards us, it encounters a massive object along its path, acting as a cosmic lens. This massive object, with its intense gravitational pull, bends, magnifies, or distorts the light from the background source, creating mesmerizing effects. There are different types of gravitational lensing, each with its own quirks and characteristics. Let's start with weak lensing. It's like wearing slightly blurry glasses. It causes subtle changes in the shapes and positions of distant galaxies. To detect these changes, scientists have to study many galaxies statistically. Weak lensing provides valuable insights into the distribution and abundance of dark matter in large cosmic structures, like galaxy clusters. It's like uncovering invisible cosmic fingerprints left behind by the mysterious dark matter.
And this leads to an amazing use for the idea of gravitational lensing. We can use it to see the unseeable.
Now, let's step it up to strong lensing. This is like a cosmic superpower that arises when there's a perfect alignment between a massive object and a distant source. Strong lensing can produce mind-bending effects, multiple images, arcs, rings, or other distorted shapes of the background source swirling around the lensing object. It's like looking through a cosmic kaleidoscope. This powerful phenomenon helps scientists measure the mass and shape of the lensing object, while also magnifying and revealing hidden details of distant sources that would otherwise be too faint or small to see. And then we have a special case called microlensing, which adds a touch of celestial drama. Microlensing happens when a smaller object, like a star or a planet, passes right in front of a more distant star. The foreground object acts as a temporary magnifying lens, making the background star appear brighter or larger as it gets lensed. Microlensing is an exciting tool for discovering planets around other stars, as well as detecting other exotic cosmic wonders, including black holes or neutron stars. And for the first time ever, something shocking inside a black hole. Scientists trained their high-tech telescopes on a supermassive black hole nestled at the heart of a galaxy a whopping 800 million light-years away. Now, black holes are known for their insatiable appetites, gobbling up everything that comes too close. Well, in this case, the black hole's cosmic feast caused something extraordinary to happen. As gas from its surroundings fell into the black hole, it became heated to extreme temperatures, reaching millions of degrees. This searing hot gas formed a glowing corona around the black hole, like an intense cosmic halo. The insane part is that these X-ray flares, the cosmic fireworks caused by the superheated gas, didn't just disappear into the black hole's cosmic abyss. Oh no, they actually had a cosmic rebound. The X-ray flares managed to escape, but in a most peculiar way. They were reflected by the gas situated behind the black hole itself. But that's not all. As if defying the laws of physics, these reflected X-ray flares then faced another cosmic obstacle, the mind-bending gravitational pull and magnetic fields of the black hole. And guess what? They survived. The black hole's immense gravity and magnetic fields bent the X-ray flares, giving them a curvy path toward our telescopes. Now, why is this so significant? Well, this jaw-dropping discovery is actually the first ever direct observation of light coming from behind a black hole. And guess whose theory gets another confirmation? Albert Einstein. His groundbreaking theory of general relativity predicted that light could be bent by gravity. This exceptional observation fulfills Einstein's prophecy, reaffirming the brilliance of his insights. But how did this groundbreaking discovery unfold? The story involved two impressive space telescopes, XMM Newton, operated by the European Space Agency, ESA, and NuSTAR, operated by NASA. The telescopes had their gaze fixed on the supermassive black hole, and they were in for quite a show. Over several days in 2018, they observed the mesmerizing X-ray flares emitted by the black hole's scorching hot corona. But here's where things took an intriguing twist. As the researchers delved into the data, they noticed something peculiar. Some of the X-ray flares had distinct colors and arrived later than others. Why? Because these X-ray flares were actually coming from behind the black hole itself. To confirm this astonishing observation, the researchers rolled up their sleeves and got into some serious analysis. They compared the data with theoretical models, running the cosmic numbers through their computations. And voila! The pieces of the cosmic puzzle fell into place, revealing that they were indeed witnessing something extraordinary. A phenomenon known as light echoes from behind the black hole. As we know, a black hole possesses an incredibly strong gravitational pull that not even light can escape. However, in the vicinity of a black hole, there's often a swirling disk of material, like gas or dust, drawn in by its immense gravity. This material heats up as it spirals toward the black hole, emitting powerful X-rays and other types of radiation. This creates a blazingly bright ring called a corona, encircling the black hole. Here's where the magic happens. Some of the X-rays from the corona manage to strike the gas located behind the black hole. But wait, how can we see these X-rays if the black hole is supposed to block everything? Well, this is where Einstein's theory of general relativity comes into play again. You see, Einstein taught us that gravity isn't just a force, it's a property of space and time itself. And massive objects like black holes warp and bend the fabric of space and time around them. This cosmic warp gives rise to an enchanting phenomenon called gravitational lensing that we mentioned before. And the magnetic fields around the black hole can also come into play, twisting the light even further in a cosmic dance called Faraday rotation. So, when the reflected X-rays from behind the black hole encounter its gravitational and magnetic fields, they get bent and twisted, making them visible to us from certain angles. Now, what does all of this mean for us? Well, this discovery is a monumental milestone as it confirms a key prediction of Einstein's theory of general relativity. It's like a cosmic high five to one of the cornerstones of modern physics. Additionally, it deepens our understanding of black holes, their intriguing coronas, magnetic fields, and the swirling disks of material around them called accretion disks. Let's not forget the power of multi-wavelength astronomy, which played a pivotal role in this discovery. By utilizing different types of radiation, scientists can explore various aspects of cosmic phenomena, unveiling the cosmic tapestry piece by piece. And now we've got an extraordinary discovery on our hands. A wandering black hole that's breaking all the cosmic rules. It's like a lone wolf, roaming the vastness of space without a galactic home to call its own. But how did our clever astronomers stumble upon this cosmic renegade? Well, they brought out the big guns, the Hubble Space Telescope, and employed a cosmic trick called gravitational microlensing. In this awe-inspiring saga, our intrepid astronomers used gravitational microlensing to unveil the existence of this wandering black hole, a cosmic vagabond drifting around 5,000 light-years from our beloved Earth. It has a mass 7 times that of our Sun and moves at an impressive speed of about 45 kilometers per second. But how did this cosmic wanderer come to be? Well, the scientific suspect is that it all started with a massive star that underwent a dramatic collapse, giving birth to this remarkable black hole. This extraordinary black hole managed to escape its home galaxy due to a supernova explosion that was anything but ordinary. It was a spectacularly asymmetric explosion that gave our wandering black hole a cosmic kick, propelling it away from its birthplace and into the vast expanse of the Milky Way. And the black hole we've discovered is actually one of the smallest ever detected. It's like a cosmic gem hidden among the stars, waiting to be uncovered by our inquisitive eyes. This discovery opens up a whole new chapter in our understanding of these enigmatic cosmic entities and their cosmic journeys. In November 2022, a group of astronomers found something terrifying. They found a black hole, and it's the closest one we've ever detected to our planet. You're probably thinking, how close? It's located a staggering 1,566 light-years away. It might not sound close in the way we think of grabbing a coffee down the road, but in the grand cosmic scale of things, that's practically in our backyard. This mysterious and exciting black hole resides in the constellation Ophiuchus. It's named after a character in Greek mythology, the serpent bearer. It's a beautiful patch of sky, but the real kicker here is what's lurking within it. Our astronomers, with their eyes fixed on the cosmos, decided to name this nearby black hole Gaia BH1.
Some of the biggest black holes ever recorded in the history of science that have gobbled up over 20 billion stars.
And Gaia BH1 isn't just some run-of-the-mill black hole, it packing about 10 times the mass of our very own sun. But Gaia BH1 isn't just floating around aimlessly in the inky black vastness of space. It's got a companion, just like the Earth has the moon. Gaia BH1 is in an orbit with a star similar to our sun. Together, they make up what astronomers call a binary system. And Gaia BH1's partner is a star that's not too dissimilar from our very own sun. It's about the same size, with a similar glow, but it's just a tad cooler and has a slight reddish hue. The first clue was a bit of a wobble. You see, the companion star, even though it looks stable from our viewpoint, was actually wobbling ever so subtly. And it was due to the enormous gravitational pull of Gaia BH1. That's right, the black hole was tugging at the star, causing it to sway back and forth, but the clues didn't stop at the wobble. Our astronomers also noticed something peculiar in the star's light. The star's spectrum, which is basically the range of colors in its light, was shifting slightly over time. This change is known as the Doppler effect, and it was a big hint that the star wasn't just swaying side to side, but also moving towards and away from us. And who was to blame for this rhythmic motion? You guessed it, Gaia BH1. By putting these clues together, the astronomers could estimate not only the mass and distance of Gaia BH1, but also how long it takes for the star to complete one orbit around the black hole. And it turns out they are pretty fast, completing an orbit in about 185 days. So what's the big deal about finding Gaia BH1? First off, the fact that Gaia BH1 is the closest known black hole to Earth is terrifying, but also an opportunity.
But now, the closest ever black hole to our galaxy has been spotted by astronomers. Should you be alarmed?
This proximity means that we have an amazing opportunity to study a black hole in more detail than we ever have before. As we create better and more advanced telescopes and gadgets, we'll be able to use them to look closer at Gaia BH1. Secondly, Gaia BH1 is a bit of a cosmic oddball. Most of the black holes we know about have these supermassive companion stars that feed them gas. This creates a whole bunch of bright X-ray emissions, making the black holes much easier to spot. It's like those stars are throwing a massive cosmic spotlight on the black holes. But Gaia BH1 is different. It doesn't have a supermassive star partner, meaning it's not creating those bright X-rays. This makes it a quiet black hole, just minding its own business in the dark corners of the galaxy. These quiet black holes are notoriously hard to spot, making Gaia BH1 a rare and exciting find. Thirdly, Gaia BH1's discovery suggests that our galaxy might be chock full of these quiet, elusive black holes. Until now, they've been really good at escaping our notice. Our astronomers have done some number crunching, and their estimate is truly exceptional. They believe there could be hundreds of millions of black holes in our galaxy. But guess how many we've actually confirmed so far? Just a few dozen. But Gaia BH1 has taught us that black holes can be different. Some might have low mass or faint companion stars that don't produce much light or radiation. They might be more common than we think, But spotting them is a whole different ballgame. We'll need more sensitive and precise measurements to reveal their presence, and that's an exciting challenge for future astronomy. And you know, the story of Gaia BH1 isn't just about the discovery of a nearby black hole. We also have a magnificent piece of space technology known as the Gaia Space Telescope. This high-tech marvel was launched into the cosmic beyond by the European Space Agency back in 2013. Now, Gaia is not just any old telescope. Its mission? To craft a three-dimensional map of our galaxy. It does this by measuring the positions, distances, motions, and properties of over 1 billion stars. Yeah, that's right, 1 billion. This brings us to another exciting revelation. Gaia BH1 is not an only child. In 2023, the Space Telescope played a vital role in discovering another black hole, aptly named Gaia BH2. This one's a bit smaller than BH1, and it's orbiting a giant star roughly 3,800 light-years away. Just like its older sibling, Gaia BH2 was found by observing its gravitational influence on its companion star. The star's motion and spectrum, again, gave away the hidden black hole's presence. So there you have it. Gaia BH1 is not just a black hole. It's a clue, a signal, a hint at what lies hidden in the vast expanses of our galaxy. Its discovery has shed light on how much we still don't know about the universe, and how much there still is to discover.